So I begin, Jennifer. The two of you, it's okay. And today we will discuss actually the most important notion of the remaining part of this course, namely notion of differential form. I said something last time, not about differential forms, but about the corresponding notion in the linear algebra. Remember, we have some finite dimensional vector space. Say a real vector space, although from the algebraic point of view, any field of characteristic not equal to 2 will work. So we have a real vector space of some finite dimension. Then we consider the dimension certainly is n, what else? Then for some number k, between actually 0 and n, we consider k linear forms which satisfy an additional condition of being skew-symmetric. Do you remember what it is? So a k linear form, usual definition, and if you switch to arguments, then you acquire the minus sign. If we have now the notation for the space, it is a space, for the space of all exterior forms, skew-symmetric linear, k linear forms, is lambda k v star. So k is a number between 0 and n, which is dimension v. V is a real vector space, and this is the space of all forms which are k linear, depending on k arguments in v, and skew-symmetric. That is, change sign when you swap to arguments. Now I want to say of the thing that if you have a linear map of v into w, the dimensions may be different. Then there arises a map which we denote as f upper star lambda k w star into lambda k v star in the obvious way. Simply we apply our map f to the arguments. And now one thing which I didn't mention last time, but which is very important. This is the so-called exterior product. Also a linear algebra notion. We have two forms, alpha and beta. Alpha is in lambda k v star, and beta is in lambda l v star. Two forms, two exterior forms. And then what is alpha wedge beta? It is again a skew-symmetric form, exterior form of degree k plus l. It is defined in the following way: alpha wedge beta applied to k plus l vectors, v1, vk plus l, is defined as the sum minus 1 to a certain degree, which I write later. Here I write 1 less than or equal to I1 less than ik, and here k plus l. And here I write v, alpha applied to v I1 v ik, beta vj1 vjl, where j's are L numbers, also ordered in the increasing order, so that Actually, they form the complement. All numbers between 1 and k minus L, which are not i's. Now here, plus minus, I need to arrange them in such a way that the resulting form will be skew-symmetric. And here I write I1 plus ik minus 1 plus k. So if i's are just 1, 2, 3, and so on k, then the sign will be plus. And then it varies between plus and minus when we move some i's to the right. So this is the right formula. The product is probably real numbers. Any comments, questions about this formula? This is sort of important. One of the most important notions, and the first, not application literary, but rather first mentioning of this formula will be made immediately, still in the context of linear algebra. After which I don't want to say forget linear algebra, we will remember it, but will not refer to it explicitly anymore. So, I said last time that the dimension of lambda k, v star is n choose k. And this has a very simple explanation. If you want to know a form alpha from lambda k v star, it's sufficient to do the following. We choose a basis in V. And we write alpha ei1 eik, where again i's are between now between 1 and n. This is a number. I denote it as alpha I1 ik. And it is very clear that these numbers determine the whole form. Because if you apply it to any vectors, those vectors are linear combinations of I1, In. And definitely all we need to apply alpha to the basic vectors. And it is not reasonable to apply alpha to set of basic vectors with repetition, because we will get 0. And also, if you switch to vectors, basic or not, you will just have the minus sign. So it's sufficient to know, if you want to know all values of alpha on sets of basic vectors, sufficient to have these values on vectors ei1, eik, with i1, ik being an increasing sequence. Okay? And now I want to make the following remark. No, you will make this remark. I choose a basis. Not choose, I already have a basis in V, and I have the so-called dual basis in V star, namely epsilon I. I can say now that this is an element of lambda 1 V star, simply a linear form on V. And epsilon I, by definition, is delta ij. So it is 1 if you apply ei, and 0 if you apply anything else. And now I want to say the following. This definition, this notion will be important to me, but still I erase this. I want to say the following, that an arbitrary form alpha, as here, is equal to the sum over all sequences I1, ik, alpha I1 ik, this alpha, times epsilon iy well, certainly I prefer not to play the algebraic games, but maybe I sort of overdo, because I probably had to say that the wedge product satisfies all good algebraic properties. In particular, it is associative. So we can actually take wedge product of several arguments. What I didn't say, and you want to know it, so let me write it here. It is that if alpha is from lambda k and beta is from lambda L, then alpha wedge beta is negative 1 to the power KL beta alpha. This follows from the skew commutativity immediately, and I will not check it, but it is true. Now I need a different thing. I want to have the right to use this notation. So this is the wedge product of k forms. K forms of degree 1, so the whole product has degree k. I do not need to write parentheses because the product is associative. Can I continue? Or you have questions, Dale? No. Very much algebraic. I don't know how much you like algebra. You do. I know everything about virtual, don't ask him. So why is this so? If I wanted to prove how to do it. This is the very, very last result from linear algebra, which I will need. So how to prove it? Maybe it's wrong? How to prove it? You know, there exists a universal way to prove that two functions are the same. You need to plug arguments and compare the results. In the case of multilinear forms, you don't need to plug arbitrary sets of arguments, especially in the case of skew-symmetric forms. To prove that this equality holds, I want to plug ej1, ejk for some values of j's. If I plug this and the results on the left and the right side are the same, then it's okay. On the left-hand side, if I plug this, I get alpha j1 jk simply by definition, which is there on the left. What happens if you plug ej1 ejk into this product? First of all, you remember the definition of the wedge product. We need to plug some arguments into one factor, some arguments into the other factor. Here we have many factors, so we need to somehow distribute the arguments ej1 ejk among these factors, epsilon I1, epsilon ik, right? We need to plug one to each. But to get something different from 0, we need to plug into epsilon I1 ei1, otherwise it will be 0. Into epsilon I2, we need to plug ei2, and so on. This is possible only in one case, when actually j1, jk are the same as I1, ik, right? And in this case, we will get 1 when we plug. In our case, we get 0. The sum of 1 and crowd of zeros will be still 1. So when we plug this, then we get only one summand. Namely, the summand where I1 is j1, ik is jk, right? And The equation is this. This equality doesn't cause any doubts. So this theorem has been proved. This is all from linear algebra, which I wanted to say. So if you have linear algebra questions, especially those of you who may teach linear algebra and want to have problems for homeworks and tests, please ask a question if you have. If you don't have questions, then I continue. We are here not to study linear algebra. We are here to study manifolds. If you have a manifold, certainly of dimension n, what else? It is not a vector space, but there are vector spaces related to this manifold. And I mean the tangent spaces at different points. All right? There are many points. Well, I don't know how many points, but still there are points. And for every point, we can consider these exterior forms. What we do now, we define a differential form. Why it is differential, we will see after several minutes. Differential form on a manifold. This means that for every point on this manifold, we need to have an exterior form of the tangent space. Plus one condition, which we will have to discuss. So, a differential form of degree k on an n-dimensional manifold. And here, the manifold is absolutely arbitrary. It is M. It may be compact or not, orientable or not, whatever. What else? This boundary or not. Still, it has tangent spaces at every point. And it is a function which assigns to a point P in M an exterior P form on the tangent space, and then I write the bottom line this alpha p should depend in a smooth way on P. It is very easy to write it, but still possible to. It is permissible to ask what could it mean. What this could mean that alpha p depends smoothly on P. Do you have an idea how to formulate this to satisfy people who prefer rigorous definitions? What this condition of smoothness could mean? Doug, we want to say something. C infinity certainly, but C infinity, there are functions, C infinity functions, and we know what it is, derivatives, all this stuff. Here we have a function whose values are forms, exterior forms. In my notes, there are 3 different descriptions of this notion. 2 of them I will give to you now immediately. The third one you can read there. Smoothness. Smoothness is something which we can apply to functions. So to explain what it means, we need to somehow to produce functions. And we have this possibility because we have these numbers alpha, I1, Ik. So the most immediate explanation of smoothness is the following. We take, so this function is alpha, obviously, p alpha p. We take a coordinate system, local coordinate system u, x1, xn. They are defined in some open set, but there are charts which cover the whole manifold. And then, for every point within the domain of these local coordinates, we have some very special vectors. D over dx1, d over dxn. This belongs to Tp. And for every p in the domain of our local coordinates, right? Okay? And certainly we can, these are vectors for every p. And we can plug them. Plug what? We can plug n vectors into k form, so we can take alpha p of d over dxi1, dx ik is usual. I1, ik are numbers between 1 and n. And this is a number for every p, right? This is a function. In the domain of local coordinates. And it must be C infinity. This definition is good, but requires some work. And certainly I will not do this work. Because there are different local coordinates. And somehow we need to check that this doesn't depend on local coordinates, which is almost obvious, or simply obvious, because the transition from a local coordinate system to a local coordinate system is at every point is done by linear summation, whose matrix is a Jacobian matrix, very much smooth. So it is not hard to understand that if it is true for some, for two local coordinates, for some local coordinate systems, and for any other local coordinate system whose domain overlaps with the domain of our system, these conditions are equivalent. Still, it is not very convenient. It is always convenient to make different computations using local coordinates. But for definitions, they're not convenient. And there exist two different approaches, of which I consider here one. Namely, I say the following. Forget local coordinates. Suppose that we have k arbitrary vector fields on our manifold. Actually, we already have definition of vector fields, and they are all C infinity. We do not need to care about that. And we can plug these vector fields into alpha, because at every point they have values which are vectors, tangent vectors, right? So we can say alpha of x1 xk is a function on M. And I said it must be for every set of vector fields. From the algebraic point of view, this is a very convenient definition. I can say, I said definition. You maybe think that that is wrong. It is not definition. It is actually this derived from the existing definition. But this could be taken for a definition. And in this respect, let us spend couple of minutes to discuss what it means. Suppose that we never studied linear algebra, and we want to, but we know some topology, different topology within the frames of my lectures. And how to define what? I want to set up a definition of a differential form of degree k. So how to do that? I say that this is alpha, differential form degree k, assigns to every set of k vector fields x1, xk on the manifold some c infinity function which satisfies the following conditions. What conditions? No, this is one form. I do not have any material to. No, product will be later. Now, a definition form without any products. So, what is my conditions? This function. So, we have k vector fields and a number. Skew symmetric. Very reasonable. If you take some arguments x, x1, xk, just switch two of them. Then the result will be the same with the minus sign. Is this all? Believe me, you will see this in a minute. This question is important. Yes, Dale, you are moving in the right direction. But what does it mean, linear? You see,
in each variable?
Yes, in each variable, yes. What is in each variable?
Linear in each variable separable.
So the sum, if you take the sum of two xk prime and xi prime and xi double prime, then the corresponding values will be summed up. And also, linear, you know, it also requires some other property. Linear over what? It is my question.
Over R?
Wrong. Linear, but not over R. Over R, it is certainly this definition is possible. And from the point of view of algebra, this definition is very reasonable, and I appreciate it. But still not over R, but over functions. If you multiply some argument, whichever you choose, by a function, then so I have some form alpha, and you multiply some argument by a function. The short notation, you understand that all the arguments are the same, but number I will multiply by f, then it is the same as to multiply the result by f. Why? Because actually this property holds pointwise. At every point, this property should hold. If you multiply for some point p some vector by a constant, then yes, by a number, real number r, then yes, certainly the result will be multiplied by a number. It is true. But for different points, you can multiply by different numbers, which means that you take a function. Smooth function simply because our vector field should be smooth. It is not reasonable to multiply them by a function which is not smooth. And this property should hold. So I can say that a differential form is a multilinear, is a skew-symmetric, yes, k-linear form in the space of functions, and k-linearity holds over the ring of functions, which means that if you multiply every argument by any argument by a function, then the result will be also by this function. If you forget to say function and say R, this definition makes sense. And actually everything makes sense. Simply this is not our subject. So this is a possible definition of a differential form. Now next thing.
Do you require the function to be smooth?
Yes, if functions are smooth, then fxi will not be smooth, will not be smooth, so it's not a vector field according to our definition. Yes, f should be smooth. F should be smooth. Probably in algebra, I say probably, but actually definitely in algebra there is a corresponding language, but we are not obliged to use it. Now, the following thing, and the answer actually, I'm eager to know what your answer will be. Do you know examples of this? First of all, we need to have a manifold.
Or it's like the,
I have a manifold. We have a manifold. And I want to have an example of differential form of this manifold. And I say that actually we have one. We discussed it. We discussed it here. We discussed certain form of degree 1. And this form of degree 1 is the differential of a function. You remember, if f is a function, then df by definition is a function which takes value on vector fields and the result is this. We just apply our vector field to our function. We get another function. And this is called certainly one argument. So the condition of skew-symmetricity somehow disappears. But all the other conditions are still with us. And this is a differential form of degree 1. What about that? Why I was interested what you're going to answer, but you prefer not to say anything. But my actual question, my desire, I want to know whether you will begin with the most trivial example. What if k is 0? Difficult to say what it is, a function of the empty set of arguments. But we have to deal with such functions in analysis everywhere. In analysis, a function of the empty set of arguments is just a number, right? Here, values of our functions are values of our different forms are functions. So what if I say that a differential form of degree 0 is the same as a function? It is something which assigns to nothing a function. Nothing is nothing, but the function is a function. So a form of degree 0 is a function. Very interesting. Now I promised this to you, and I can keep my promise. Not always is possible. I wanted to say to you why these forms are called differential forms. Probably I do not know. My experience of teaching calculus is almost 0, but maybe you have more experience. I do not know whether people ever pronounce the word differential form in plain calculus. Say if you consider integrals, surface integrals, over a surface, then you integrate what? You integrate something which you call expression, but I maybe said to you, maybe not, but I do not know what an expression is. So if you understand it, that's okay. I don't understand. But if you, say, consider in space an integral over a surface, you say integral, then some notation for the surface below the sign of integral, and then the integrand. You write p dx dy plus q dx dz plus r dy dz, right? What is this? P dx dy plus q dx dz plus y plus what? R dy dz. You can call it however you wish, but usually in calculus it's called a differential form, and it is plainly differential form because there are differentials, right? Now I want to have something. For differential forms on manifolds. Suppose that we have local coordinates. Actually, I consider manifolds, but everything can be restricted to a domain. So my considerations are, in reality, local. I can, when I speak of function, I can speak of function given locally. So we have some domain of local coordinates, x1, xk. x1, xn, excuse me. Very interesting. But these x's are functions, actually, right? Functions on the domain of this local coordinate. Functions, then we can consider differentials. What is dxi applied to the vector field d over dxj? This you can say, because we have a definition. What happens, my friends, if you take the derivative of xi applied to d over dxj? What will we get? d over dxj applied to xi, dxi over dxj. But this you must know. Partial derivatives, no. It is 1 if I is equal to j, and 0 otherwise. No problems, right? So this is delta ij. Now, so dxi's, dx1, dx2, dxn, form a basis in the space of linear forms in the tangent space at every point, which is dual to the basis which we usually use, d over dx1, d over dxn. By this reason, I can write that an absolutely arbitrary form alpha I consider only within a domain of local coordinates is equal to the sum 1 k is the degree of this form. Here I write alpha applied ik, and here I write dxi1 dxik. And this is precisely the result which was mentioned, mentioned in the beginning of my lecture. This expression alpha of dx1 dxk, I can use some notation for it. So let me write alpha I1 ik. And it is a function because it has a separate value at every point. So every differential form in local coordinates have this presentation. And this you know. For example, imagine that your manifold has dimension 2. Coordinates are x and y, what else? And we have a differential form of degree 1. What is this? How to express it in this way? Two functions, alpha 1 and alpha 2, that are more commonly denoted as p and q. P dx plus q dy. See it here. What is the differential form of degree 2 in the plane? Some function, you can denote as p or r, whatever, times dx wedge dy. Right? What is a differential form in 3 variables? Say in R3, in domain in R3. Say degree 2. You're right. P dx wedge dy. P is a function of x, y, and z. P dx wedge dy plus q dx wedge dz plus r dy wedge dz. My friends, is it clear? Somehow we consider manifolds and then we descend. We go down, 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 down to the bottom of mathematics. And there at the bottom we see this expression p dx plus q dy. And this is a differential form of degree 1 in a space of 2 variables, like the domain in the plane. Comments? How does this do? Is it clear? Differential form is this, p dx plus q dy. P and q are functions of x and y. P of x y dx plus q of x y dy. And this is a differential form degree 1 in a domain of local coordinates x and y, simply domain in the plane if you wish, where this differential form is defined. Do you have questions? Remarks? Because I want to use the remaining 2.5 minutes to say something about our future exercises. So now we have this coordinate expression, which may be useful for differential forms. Differential form of degree 0, no differentials at all, just a function. Differential form of degree 1, one differential. This wedge, usually not used in calculus, and really I do not know how they deal without this, because dx wedge dy and dy wedge dx is not the same. Dx wedge dy is equal to minus dy wedge dx. And in calculus, certainly people say some strange words about orientation, about the integral depends on the orientation and so on, which is difficult to understand because they do not make much sense. But they prefer not to use this symbol wedge, which is actually the most important in this theory. Now I want to formulate a certain result, which we will prove next time, but still. We have differential d, which you use at the moment. In the following context, they are differential of functions. By the way, notation which I am going to use, omega km. This is the space of differential k forms on M. And this differential, which I'm going to erase now, is this. To zero form the function, we assign one form. Actually, in this theory, the most important notion is the notion of differential. But the differential will act from omega k m into omega k plus 1 m. For every k. And it will satisfy the following three conditions. First, if k is 0, then this is this. Second, d is 0. If you apply d to a differential form and then apply d once more, you will get 0. And third, the product rule, which you mentioned, Virgil, d alpha wedge beta plus negative 1 to the power k. K is the degree of alpha. Alpha wedge d beta. So these three simple rules, very much algebraic. Fully,
The chain complex?
it is a chain complex. You can say cochain if you prefer these additional two letters. Yes, it is a complex. We will consider homology. It is my main goal. But so far, no chains, no complexes. We have differential forms, omega km. There will be this differential. The square is 0. The rule very much neglected in calculus. And also the product rule. This is all.